course on reasoning about a highly connected world. This is about networks, internet, but it's not a networking course like Olivier Bonaventure. It's a course about how human beings interact on networks, social networks. So it's not only computing, it's also sociology. Yeah? So you didn't expect to be in a course on sociology. It's based on this very nice book, which is required. Most of the material is on the slides, but sometimes the slides are a little bit brief, concise, and this book has lots of good explanations. It's very well written, has lots of nice things, so it's all explained in here. So this book, there are some copies in the library. You can also buy the book, okay? And if you buy the book, you can also download the PDF, okay? So I have bought the book, here it is. So I have a legal PDF of this book as well, okay? So actually it's a very good book, and I recommend that you buy it. So I can pass it around if you want. People want to look at it during the lecture. But in fact, you should, networks, I will show it. Okay. So this book, this course is about networks with many participants. So it could be social networks, could be the web, or even the general internet, whatever. Even human networks, friends between human beings, any kind of group of people where some of the people are connected, okay? The people connect with each other and with the network. So maybe there's, on the web, for example, you read web pages and you get information. But information also travels through outside of the web when people talk to each other, okay? So there's multiple ways that the information passes. So that this can be actually somewhat complicated. There can be unexpected effects. So I will talk about cascading, tipping points, stable things, unstable things, places in the network where you have a lot of power, places where you are very weak, and how we can predict what happens. So with this course you will, I hope, really get a much better understanding of how the internet is actually working for people, okay? So we're going to focus on two special cases, internet, of course, in general, but also web, but it also just networks of friends, people knowing other people, okay? And there are 4 topics that we will introduce. So I will talk about graph theory. This you already have maybe a little bit. I will talk about game theory. I'll give you an introduction to game theory, very interesting. Also a little bit of economics, market theory, and some sociology. It's all connected together, okay? First, let me explain how we're going to organize this course. So there's a Moodle, of course, so everyone should be enrolled on the Moodle. There's one lecture every week, so this is the first one, Wednesday at 2 o'clock. There is a practical lab session. This is Monday at 4:15, and there's 2 parallel sessions, BART 91 and A03 in Science Building. This is very important because this material is, I think you have never seen it before. So it takes a little bit of time to really get it, okay, to understand it. So it's important to be present in the weekly lab sessions, okay? In order to encourage your presence, I will create what's called a small bonus. So the teaching assistants will note your presence in the lab session and will count how many lab sessions you're present. And if you're present in all of them, you will get 1 extra point on the exam. Not bad, huh? Just for being there and trying to do exercises. So this is actually a double benefit, because the fact of being there will already improve your points also. So this will improve your score in 2 ways if you do that. Okay? So this is a true bonus. That means you can theoretically get more than 20 points on this course. I have seen people get 20.5 or something. Okay? Of course, I have to round down to 20. I can only give maximum of 20. So that's one thing, to encourage you to attend the lab sessions. So of course it's important to attend them, and you should know that now, but I know it's very hard every week to move yourself from your comfortable comfy chair into this harsh lab environment. So this encouragement I hope will help. Okay. So other than that, there's a midterm in the middle worth 5 points, and this is optional, you don't have to do it, no penalty if you don't do it. There is a project in groups of 2 in the second half. This one is also worth 5 points, but this you have to do it. If you don't do it, you will miss these 5 points, okay? And then there's the final exam, worth 15 because of 5 in the project. Note that the midterm corresponds to one of the exam questions, and I will take the maximum of the 2, okay? That means if you do very well on the midterm, you can consider that you can skip part of the exam, okay? So if you do very well on the midterm and the project, you maybe have already succeeded in the course, okay? Now, the project also, usually everyone does pretty well. You get plenty of time. This will be something where we put into practice some of the ideas on networks. So you'll have plenty of time to do this. So usually it's in the last third of the course, but students, they keep nagging me, bugging me to give the project description before Easter vacation. Now I'm very nice, I don't like people to work during Easter, but some students, they persist in wanting to work during the Easter vacation. So I'm not going to, this is actually, I don't mind that, okay? So you will have 2 weeks on the project, but not counting the Easter vacation, of course. So normally everybody should do very well on the project, I hope. Okay? So my goal in this course is that you learn the material. I hope that's one of your goals too, but I'm sure another of your goals is to get good points on the course. And what I try to do is make both of these goals they coincide, so that one is the same as the other. So there are 2 teaching assistants, Lucille Dibs and Jean Gina, who will be managing the project and also the lab sessions. So if you have questions, you can always ask them or me, okay? So that's how the course is organized. Now, I have to warn you, this is actually a very new and material, which is not like what you see in many courses, because it's not just purely technical, there's also some humanity aspect. So it takes time to understand it. So I really recommend that you attend the course every week. Even if you don't pay so much attention, it will go into your subconscious mind and it will help you. Okay, so that's the course organization. So I'll explain now the schedule. We're going to start with some introductions. We'll start the first weeks by talking about graph theory, and I will introduce a lot of graph notions. Some of it you've seen it already, and also how it connects to social networks. So paths, connectivity, strong, weak links, closure, friends of friends become friends, positive, negative links, friends and enemies, or trusting something and not trusting something. And then so that's the first 3 weeks, and then in weeks 4 and 5 we'll talk about game theory. So this is very interesting. So it's just an introduction that I'm giving you. What is a game? Maybe you have already heard or seen something about game theory. Well, here we're going to actually talk about strategies for games, how these games appear on the networks, and how you can solve them. And sometimes you get funny paradoxes, like the race paradox, where if you have a highway on this, and if you add a lane in the highway, it can actually reduce the maximum flow. Okay? Why is that? That seems paradoxical, how can that be? And in fact, there's famous examples, like in Korea, in Seoul, the capital of Korea, they actually was a big lobbying to build a big park in the center of the city. And in order to do that, they had to close down part of the highway. People were complaining and everything. So they built the park, they closed down the highway, and the traffic into the city improved. Okay? So this was like really win-win. So this kind of thing, which is like paradoxical, we're going to see it in this course. Okay? So that's all part of game theory. We're also going to talk about markets. So that's economics, buying and selling, making things, selling things. So you have buyers and sellers, and how do they determine the prices? So this is a lot of what happens on networks in the world, but also on the internet. And then you have some concepts there, like market clearing, which is basically a very sophisticated term for supply equals demand. So when I build a product, if there's too many buyers, I will build more, or maybe raise the prices. Okay, so there's kind of an equilibrium that's going on. There's also bargaining, where everybody tries to get a little bit the maximum of things. Okay, and that happens a lot on the network. That will keep us for a few weeks, and in the final part of the course, we're going to apply things to the network, the web, the page rank, how that search algorithms work, search markets, how Google makes money, okay? Information cascades. So somehow if you're the first person to do something, it gives you an advantage. So there's, and this depends on the network. Network effects where if, for example, you have more people doing something, it's better. It gets better. So the more people that use Android, the more apps you get on Android, okay? So you as a user, it gets better for you if there's many users. So this is called the network effect. Also structural cascades, where somebody can block something in the network, but if that person changes their opinion, then things will go on. For example, also things like small world phenomenon, 6 degrees of difference, how that everything is very close. In fact, all these networks actually, things are much closer than you might imagine. So you see, all of this is kind of very weird and so on, but we're going to see a very nice, coherent approach for discussing it all. Okay? So the book here, this is the mandatory, the syllabus for the course by David Easley and John Kleinberg. There are some copies in the library, so I recommend that you buy this book. You have some copies in the library that you can get. Of course, you could probably succeed in the course just by looking at the slides. And of course, I will be making videos, so these videos will be on YouTube. But actually, it's a really good book. So even if you, after this course, this book will be a help for you, okay? So we're going to see different chapters in the book. And it's all, this course is actually very closely connected to the book. The graph theory is chapters 2 to 5, okay? The game theory is 6, 8, and 9. So we're skipping some chapters. The markets is 10 to 12. And the internet, the web, is 13 to 20. And there's many other things in the book that we don't see. There's also advanced material in the chapters. Usually we don't see it. So we're only actually seeing like half of the book. Okay. So that gives you the structure of it. Let me now, this first lecture, I want to kind of warm up. I want to give you some examples, some intuitions, and which is called like a teaser. I'll give you some little things that will get you thinking about the course and to see what the kind of things we're talking about. So the first thing I want to talk about is graph theory. And you see, these examples, actually, many of them are coming from the book. I've also taken a few other examples. So here's an example. Each of these circles is a person. They're numbered, but it doesn't matter. It's just to have a graph. And there's an edge, a connection between two people if they are friends. Okay. So this is 34 people. And this is actually a karate club. So this is actually in a publication. All of this is some stuff that you can look up in the Journal of Anthropological Research. Okay, so this is anthropology or something. But here's a karate club of 34 people. Okay, so you can already deduce some things here. Number 34 has a lot of friends. Okay, you can see that. Also, number 1 here has a lot of friends. And then the others, it depends. Like number 2 has a bunch of friends. Some people have very few friends. Number 19 doesn't have so many friends. Okay, doesn't matter. Number 12 is only friends with 1, doesn't know anybody else. Okay, so this gives you kind of a view, an abstract view of the people in this karate club. Okay. Now, how can this help us? Actually, this kind of a structure can help us predict what's going to happen. So here is something that actually happened in this karate club. The club split into 2. And a bunch of people left the club to make another club. And all these people were the people around number 1. So somehow 1 and 34, they got into some argument or how the karate should be taught or whatever. And so the 1 decided to leave and a bunch of people left with number 1. You can see that 1 and 34 are not friends, okay? There's no line between 1 and 34. So 1 just left, taking with them a bunch of the people. And so all these gray nodes, they became a second club. So that's kind of interesting, huh? But you could actually predict it from here. If you look at this graph, you can see that you can actually deduce things. You can actually predict that 1 and 34 are like 2 centers, and that there's no friendship between them. So this should not be completely unexpected, okay? See, so this gives you kind of an example. You can use the graphs to understand and predict things, okay? Okay, that's a simple example. Here's another example. Financial institutions. Okay, so this is a very complicated graph. You can get all the details, but there's actually thousands of banks. Every node on this graph is a bank, okay? And there's a link between the bank when the bank owes money to another bank. So banks, their business is buying and getting people's money and making loans and so on, and they live off of the interest and the investments and so on. So if a bank does not have enough money, on one day it takes a loan from another bank, okay? That's quite normal. And this happens, and banks are big organizations usually, so usually there's many, many loans. So in fact, you can have cycles in this, where bank 1 owes 10 billion euros to bank 2, bank 2 owes 5 billion to bank 3, and bank 3 owes 7 billion to bank 1. Well, you see this and you say, why? Well, I mean, why don't they just fix it? And because, I mean, it's kind of funny that the loan is in a circle. But you can't really change that, because each of these loans, there can be many small loans here, and they can be over different time periods, with different conditions, etc. So this situation happens a lot, okay, where you have these cycles. And if you make a graph here out of it, you can see that this graph has what's called a strongly connected component. In a graph, a strongly connected component is a part of the graph, subset of the nodes, such that there is always a path between any two nodes. So it's a subset of nodes that are kind of all connected to each other. So it turns out, if you look at the actual financial structure of the Earth, okay, of all the big banks that we know, you get something like this. You have some banks that are owing money to that, but in some banks that they are owed money, and they're not part of this. But the central structure where you have these cycles is actually huge. Okay? Now that's very interesting. We can deduce many things from that. One of the things we can deduce that it makes banks fragile. It's like dominoes. If Bank 1 goes bankrupt, well, then Bank 2 will never get these 10 billion euros back, okay? And maybe Bank 2 will also go bankrupt because of that, because it's a lot of money. And then Bank 3 will never get the 5 billion. You see what I'm saying? So that what it means is that there's all these dependencies, these connections. If one of these banks defaults in this strongly connected component, all of the banks it's connected to are stressed, are put into some kind of difficulty, okay? It's like dominoes, huh? When one of them falls, many can fall, okay? So this is why people talk about banks that are too big to fail and so on, huh? Because if a very big bank fails, it might pull down many others because of that. Now you might say, but that's artificial because you could reimburse all of this and then there would be no connection. Yeah, that's actually not so easy. So one solution, of course, is to try to do some of that to de-stress the system, okay? To remove some of these circular dependencies. But if you don't have some government regulation, then you will get these. So this is all individual banks, okay? So you have always a stress between individuals and society. Individuals try to maximize their well-being or their profit, but they're very selfish. They don't care about society. They want to make good salary or whatever, huh? And here the banks want to make a profit. And if the bank needs to make a loan in order to get good profits, we'll do it, huh? Whereas society looks at all of them and says, this is maybe not a good idea, okay? So that's another tension between individual selfishness and general ideas that are good for everyone, okay? So there's some compromise that you need to do, right? You can't have 100% government regulation, doesn't work. That would be like communism, never worked. But you cannot have raw, savage capitalism either, because people would suffer a lot from that too. So you need something in the middle. And that's something we will talk about in this course, okay? So this has nothing to do with politics. This is purely graph theory, okay, and sociology. Okay, so you see, it's nice, huh? So this kind of stuff we will be discussing it, okay? Okay, that's a teaser for graph theory. Let me now give you a teaser for game theory, which is a different topic, totally different. So what is game theory? Well, game theory, so these are games. So there's actually a formal mathematical definition of a game. So there's a fixed set of rules, and you have players, and a player at each step will make a move. It will decide to do something, and the other player will decide, and the result depends on the combination of both. Okay? So that's the kind of the thing. The players, they interact, and each player's outcome depends on the decisions made by others. Okay? So I might decide to Like there's many different possible games. I might decide to, if you have two countries, country A, some eastern country with some kind of an autocrat decides to make some kind of aggressive move. Country B, I'm naming no names, but it starts with a U, okay, tries to defend itself and brings in other countries, and that changes the situation. So there's a payoff. Which one gains? And then there's another step, and so on. So there's a kind of sequence of operations, of moves, and depending on how the game is organized, then the players will get a win or a loss. Okay? So this is a very general thing. You can apply it to games for fun, chess or checkers or whatever. Poker is a nice one. But in fact, you can apply to many, many situations. For example, companies that have products on the market. If I put a product and I choose a new product and I'm choosing the price, that's a move in a game. And the other company, my competitor, will see that and will change the price. That's another move. And then things happen, and then the companies do more moves, okay? Pricing products, when companies sell products. Or bidding in an auction, okay? If you have not been in an auction, you have probably seen auctions, for example, in James Bond movies and stuff like that. The buyers are competing for an item, and they see each other, or maybe not. You can have public auctions or secret auctions. And the goal is to try to get the item at the lowest price, but you have competitors, okay? Or even routes on a road, cars. So the car decides to take a certain highway. That's a decision. Another car makes a decision. And then there's a result. The highway might become congested or not, okay? So there's a result depending on these two independent decisions. So car sharing roads. This is the Brest paradox I mentioned before, is a consequence of this kind of a thing. It can also happen on networks, packets being routed on networks. So you can use game theory to understand certain things that happen on networks, okay? Another one is power politics of countries, okay? This one, it's very easy. Just read the newspaper and you'll find the latest game there, okay? It's mostly a game, that's going on. So there's always this kind of a game too, okay? So we're going to see that in this course. Many players, complicated things. But I want to show you one example now. Later we'll see many more examples. Here's a simple example, although maybe you might think it's not so simple. So this is you and a friend. Both of you are students. And you're working together. So you're partners, okay? And you have two things you have to do. You have to make a presentation together, and you get points on it, and each individually has to do an exam, okay? And you have to decide what do you do today. Okay, so you and your partner today have to decide what to do, because tomorrow you will have a joint presentation and an individual exam. So what do you do today? Well, in this example, there's two possibilities. Today, you either study for the exam, forget the presentation, or you prepare the presentation. Okay? So studying for the exam is like a selfish thing. It increases your points in the exam, but it makes the presentation worse, Whereas preparing the presentation helps also the other person, but maybe worse points on the exam. So here's you make some numbers attached to this. So on the exam, if you study, you will get 92%. Not bad. But if you don't study, you will get less, but still 80%. Okay? So this is one thing you have to know. For the presentation, you have the following rule. If both of you prepare for the presentation, then it's really well prepared. You get 100%. Both of you get 100%. Okay? But if only one of you prepares and the other one does the exam, then you get 92%. But if both of you are selfish and only do the exam, you get 84%. Okay? And the total grade for each person is the combination. That's the average of the exam and the presentation. So the question, what do you do? What is the approach that will let you maximize your points? So we assume that each student wants to maximize their score, okay? And we assume that each student decides independently, okay? So this gives a table, but let me explain the table. So let me explain here how we come up with this table and what it means. So we have a table which is called a payoff matrix, okay? Here. And in this payoff matrix, there is you, your side, and then there is your partner, okay? And the two people. And you can decide to prepare the presentation or study for the exam. And your partner also can decide to prepare the presentation and study for the exam. Okay? So you have a decision. So this is like a move in a game, huh? And your partner makes also the decision. So you are sitting at home in the evening and the day before, and you're thinking, and you say, okay, I'm going to do this. And you prepare the presentation or whatever. And the next day, so you're both doing that independently, yeah? And the next day, you will have the presentation and the exam. So the payoff matrix for each of these possibilities, so there's 4 possibilities, huh? Your decision and your partner's decision. For each of these possibilities, there's actually 2 numbers. So the first number is your payoff, and the second number is your partner's payoff, okay? Like that. So each of the boxes in this payoff matrix has 2 numbers, which is your payoff, the percentage you will get, and the payoff of your partner. Okay. So the numbers are there, but let me explain how we are going to, I can compute this. So these numbers are actually computed from what I have here. Okay. So for example, let me explain how these numbers are computed. Okay. So your grade is the average of the exam and the presentation. Okay. Well, for the exam, we have this. Okay. So let me first look at the exam. Okay. Okay. For the exam, presentation, exam. So, if I study, I get 92%. If you study for the exam, you get 92%. Otherwise, you get 80. So what that means is that here we get 92. If I'm studying, then the first part of this pair will be 92. See that, huh? Whereas if I do the presentation, I will only get 80. Okay? That's my score. Okay? And the other guy, it's the same. So if the other guy does his exam, then he will get 92. So let me make it color to make it a little bit easier to understand. So you can see that you look horizontal and vertical, huh? So this gives me the payoff for the partner 2, whereas this horizontal is the payoff for number 1. Okay? So this is person 1, this is person 2. Also, this one is 80. Okay? So for the exam, if it's only an exam, we would have this payoff. You see that? If both do the presentation, both will get 80. But that's one thing, but we have also the presentation. Okay? And here it's a little bit more subtle, because here it depends on whether they work together or not. Okay? So the presentation, if both prepare, you get 100%. So that's very nice, huh? That means if both prepare, they both get 100%, like that. Whereas if only one prepares, you both get 92. So this is the one prepare case, that EE or EP. That this is 92. And the case when both do the exam, well, nobody's preparing, you get 84. Okay? So this is the payoff for the presentation. So the total, the result, the final result is going to be the average, because you do both presentation and exam, okay? So here you will get 90, 80 plus 100 divided by 2, again 90, so I'm doing the average, 80 and 92, so the difference is 12, so that makes 86. Both of these are 92, 92, 92. Here we have 92, 92. 80 and 92, so the difference is 12, so that makes 86 again. 92 and 84, so the difference is 8, so that makes 88. And here 88, okay? Okay, so this is the total payoff matrix. So this one should be the same as that one, huh? So you see how I get the numbers, huh? Those numbers are actually coming from this. It's the payoffs for everybody depending on the decisions. Okay, and now we have the payoff matrix, okay? The total payoff matrix, which is there. That's correct, huh? If there's a bug, you have to tell me, yeah? And now we decide. Now we go into the theory of games, the game theory, the mathematics. What do you do? For you, you have this choice. Your partner has this choice. What do you do? Well, you can actually reason about this table. So let me go to the next slide. Okay. Okay. So let's look at my decision. Me, I have to decide presentation or exam. So I will always get. No, okay. It could be also the other way. Let me follow this. What it says here. Okay. Assume my partner is preparing. So the partner is here. Okay? And so that means, fortunately, I don't have a stick that will point to the board. Oh. Well, let me maybe do it like, no, that won't work very well. No sticks here. No stick I can use. Let me try, okay? Here, okay? So my partner chooses presentation. So my gain will be either 90 if I choose presentation, or 92 if I choose exam. See that, huh? So if my partner chooses presentation, then I have to choose me between presentation and exam, and I will either get 90 or 92. So clearly, if my partner chooses presentation, I should choose exam, right? Because it's higher. You see that? Everybody sees that? If my partner chooses presentation, I'm looking at the first part of this, which is my payoff. I don't care about my payoff. So if my partner chooses this column, then 92 is bigger than 90, so I choose exam. Okay? But what if my partner chooses exam? Well, then I'm in this column here, and I look at the first element, and I see it's 86 versus 88. Okay? So again, I should choose exam, because 88 is bigger than 86, right? That's correct, huh? So it seems that whatever my partner does, I should choose exam. Okay? Now this is a symmetric situation, so the partner will have the same conclusion. Okay? So the partner also should choose exam. Right? Well, and then the result will be 88, 88, right? So if each partner chooses the best result for them, the final result will be 88, 88. You see that, You follow the reasoning? Now, this is very strange, actually, because if both partners would have chosen presentation, they would have gotten higher points, 90, 90. So following their selfish reasoning, they actually do worse than here. If they would have somehow said, let's both do presentation, they would have gotten both 90 instead of 88. So this is a little bit weird, isn't it? So this is actually a famous kind of paradox of game theory. It's also called prisoner's dilemma, which we'll talk about later, is that selfish decisions can lead to bad results, suboptimal results. But how could we? But we are being completely rational here, huh? You see what you follow my reasoning, huh? It's completely reasonable, and this very rational way of thinking ends up with 88. It's funny, huh? Whereas if we would somehow, if each partner would say, no, I'm not going to maximize my thing. This is actually each partner's, if my partner chooses presentation, then exam is better, and I would get 92, okay? You see that? So this is actually the best for both, but in fact it's worse. Interesting, isn't it? What do you think of that? So this is a typical kind of situation that happens in game theory, okay? So this is just a teaser today, huh? I'm not going to give you the solution to this problem. So this actually shows that strategic decision making is not that simple somehow, huh? It really depends, okay? And making rational decisions can give worse results. Interesting, isn't it? So this is a typical paradox of game theory. And we will study this, and you will understand it, I hope, very well later in the course when we get into this, okay? So this is just a teaser. So I'm not going to give you the solution to this puzzle. So how can the partners do it? So normally the partners in real-world situations, usually people will make decisions by themselves, okay? What this is showing is that can be very bad, huh? Okay? Being rational can actually be very bad if it's only you deciding, huh? Okay? So there's a little teaser on game theory. Let's now talk about markets. Let me make a little teaser on markets now. So all these little things we're going to go into them more, of course, later in the course, huh? Okay, so markets, of course, are a very big thing, huh? And internet commerce, trade. It's basically buyers and sellers. People exchanging things. You buying something on eBay. For example, I guess many people have bought something on eBay, right? Who has bought something on eBay? Or something similar to that? No, not so many. Or things like Rakuten or Prime Minister or Deuxième Main, whatever. There's a bunch of things. But in eBay, there's an auction mechanism. You know that? Enchère. So the auction mechanism on eBay is actually very interesting. And we're going to analyze that in this course. In some sense, it's an optimal mechanism. It's called a second price auction. So on eBay, if you make an auction, okay, and the price, and you are competing with somebody, and you win the auction, the price you pay is not the bid you make, but it is the second highest bid. If you look at eBay, you see that's exactly what happens. In eBay, you put a maximum. Let's say I'm buying a book, and it's 10 euros. I say, okay, I want to make 30 maximum. And I'm bidding against someone else who I don't know, some other person. That person also has a maximum. So the bid goes up. But then it stops at 15. Okay? Because the other person has bid 14, But since my maximum is 30, mine goes a little bit higher. And this is all automatic. eBay does it automatically. That means when I buy the book, so I win the auction, when I buy the book, I'm not paying 30. I'm paying 15. So basically, almost the same price as what the second person bid. That's kind of weird, isn't it? So on eBay, you don't actually pay the price of your maximum bid, you pay the price of the second bid. And that's actually very important. And that has very strong properties. It actually means that my bid is optimal in a sense. Okay, there's some optimality. So that's actually a very good auction strategy in general, on the absolute terms. It seems very weird, eh? Why is the second price so important? So the guy who invented that, or discovered that, Vickers, so he won Nobel Prize of Economics for this, okay, some decades ago. So this, and now it's every day on eBay, okay? So that's something we're going to talk about. So buyers and sellers, web, internet. We're also going to talk about geographical networks. This is like in a city, you go to a store. If I want to buy something, I go to a store. Brico-Rama or whatever. I want to buy something to whatever. I don't know what today's in France it's Leroy Merlin. So you buy. I want to buy something for do it yourself, and so there's a store. So this is my local trader. But that local trader has power over me, because if I go to another city, I will find another trader, and in fact, usually maybe that's too far away. But if I have two traders that are close together, they will compete and the price will go down. But if I only have one trader close to me, at one store, that trader has like a monopoly position with respect to me. You see the intuition, huh? So the price can be higher. So that's an intuition. But we're going to see how that works, okay? And on the network, that's very, very common, huh? On social networks, who do you know? Maybe you know some kind of a store, but you don't know some other store. So the ones you don't know and the ones you know have power over you, okay? So we're going to study that, okay? Intermediaries, bargaining. Bargaining, here's an example. I buy a house. I'm looking for a house. So I go to a house and I discuss with the housing agent. But there's a second person also wants to buy that house and discussing with the agent. So I'm actually in competition with that second person. But that second person is also interested in a second house that I don't know. So in fact, I'm not in the same situation as that first person. That second person actually has two houses they're interested in. And that means the second person has more power. Because if the agent says no, then the second person says, I don't care, I have a second house, okay? I can always buy the second one. And the agent goes, oh, I prefer you buy my house, so I lower the price a little bit, okay? So this is a graph, okay? This is kind of a graph, huh? So if I make the graph, it kind of looks like this. So here's a house, here's me, and I'm looking at this house. Here is my competitor, you, who is actually interested in these two houses. Now, and so you have an agent here, who I discussed with. I only find one house that's interesting for me. So that means the agent has power to raise the price. Whereas you have two houses. That means the agent has less power. Okay? That's funny, isn't it? I mean, that seems very intuitive. We're going to study that in this course. We're going to formalize that. And on networks, this happens all the time. Because you have some kind of a graph, and some people know things that other people don't know, and so on. Huh? So this kind of thing, where the price depends on the network. You see the kind of thing, what's going on, huh? So this kind of thing, we're going to discuss it, okay, in this course. Okay, so that's an example that we're going to discuss. The power in the bargaining depends on your position. So it's always good when you are bargaining with somebody to have a second option, huh? Because that gives you leverage. Okay? That's very intuitive. It's good advice, you see? I will send you my bill for this advice, huh? I'm like a consultant and you're learning from me. And the things that you learn from me will let you become millionaires, maybe. And hopefully you will think of me and give me a percentage, okay? No, but this kind of thing, so that's a joke, but this kind of thing, it's important because it lets you understand how things evolve, huh? So I'm not especially a capitalist, huh? Usually, professors are usually not big capitalists. But it's part of society, and economics is kind of an important thing that makes society run, okay? So it's important to understand it. And this is a combination of graph theory, game theory, and sociology, because there's a human psychology in there. Interesting, huh? So that, we'll see it in the course, okay? So here's another example, stock markets. Now this is, of course, super in the news because of cryptocurrencies and trading and so on. But this is a general thing. So a stock market is a market where you can buy and sell stocks which are shares in companies, okay? And the value of a stock depends on whatever you pay for it, okay? It can vary a lot. So you have sellers. I'm selling my stock. I'm Elon Musk and I want to sell 1 billion euros of Tesla or whatever. And then you have the buyers, which are the idiots who are going to buy that junk, okay? And in between you have the traders who manage this situation, which is like the stock market, okay? This is called an order book. So there's a lot of interesting things going on. So here on the left, okay, I have 2 sellers. One of them wants to sell at $5.50. The other wants to sell for $5. So that's called an ask. Okay? So I'm asking somebody to buy it. So this is the stock market terminology. Okay? So the lowest is $5, whereas I have people wanting to buy Shell. Of course, I don't want to pay $5, but I'm willing to pay $4 for a share. Okay? So that's called a bid. So I bid $4, and there's another bid for $3.50. Okay? So in this case, on the left, there's a difference between the lowest ask and the highest bid. So nothing happens until the ask maybe will lower a little bit, the bid will higher a little bit. Okay? But there's another thing that could happen, which is in the B in the right here. The trader is the guy sitting in the middle, is handling all this, is in a very special and very nice position because the trader could profit from both the sellers and the buyers. So the trader says, oh, okay, let me buy these shares at the ones that are $5. Okay, I know none of the buyers are going to buy it, but let me do it. So why is the trader doing this? Because the trader is maybe manipulating a little bit the market and knows that later on he's going to do something that will cause the price to go high or something up. So this is called a market order. So the trader can do stuff also. So this happens a lot in stock markets. And these specialists that do this are called traders. And this, the data structure that shows all that is called an order book. Okay, so this is all the terminology. And traders, if they're very smart, they can make a lot of money off of the buyers and the sellers because of their privileged position. Okay? So these are called market orders. And so if you want to buy something, let's say you want to buy some Bitcoin, please, I recommend you talk to your bank and they will put you in touch with the trader. Whatever happens, the trader will make money, you might not. okay? So this kind of thing is, it's important to understand this, okay? How prices between the two sides are connected, okay? So this kind of thing happens all the time, of course, on the network. Huh? Okay. Okay, let me make a small break now, and then I'll show you more stuff, okay? On va faire une petite pause. Now, has been growing for a long time. I guess around 30 years. Started in the very beginning, around 1990. So that's the 30 years. And it's no central organization. It's just growing, built on top of HTTP, on top of the internet. So the internet also was growing, and it's growing and growing. So you have this huge graph of web pages. Each page points to other pages. So what is the structure of this graph? Nobody designed it. It's purely organic. It grew because everybody in his little room is making web pages, okay? So it's completely organic. So this was a very important question. So people studied this, and this is what they find. The web has the following structure. The web is, of course, a directed graph. Each web page is a node and with some file, and there's a link to another node, which is a directed edge, okay? So it's a directed graph, a very large graph. This figure was done in the early 2000s by a guy named Broder. And in those days, the web was only 200 million nodes. Today, it's like 10 or 20 billion nodes, but the structure is the same almost. Okay, so this structure is organic. So what does it look like? It's very weird. This structure is called a bow tie structure. A bow tie is something that you put here, and it looks like a bow tie. In French, un nœud de papillon. So this sort of looks like a bow tie. In the middle, you have a strongly connected component. That means a large part of the graph, such that there is a path between any web page and any other web page. How does that work? Notice it's there, okay? The strongly connected component. And on the left, you have also a very big component of nodes that are only going into the strongly connected component. So the strongly connected component is nodes that are connected like in cycles, okay? Whereas the in part is completely directed. So if you want to make a little bit of a graph here, so in the strongly connected component, you would have things like this. There's paths between every nodes, whereas the in part has only nodes going into this, okay? And no others, okay? So this would be the strongly connected component, and this would be the in part there. And there's also an out part with nodes that are starting in the strongly connected component, but they leave out, but they never come back. Okay? This sort of looks like this. So if you want to get some intuition, it sort of like this. Here, all the nodes are connected. Between any two nodes, there's a path, okay, between them. In the in part, that's not true. The nodes are going in, but they don't come back. And in the out part, the nodes are coming from the strongly connected component, but don't come back. So those are the main parts. But they're not the only parts. You have these funny things called tubes and tendrils. Okay? A tube, well in French it would be almost the same. Right? The tube, the tuyau. And tendril in French would be something like debris. Something weird. So a tendril is something that comes out of the in part, but doesn't really go anywhere. Okay? So this would be a tendril. Or there's another kind of tendril which goes in to the out part, like this, but doesn't come from the STC. So these would be tendrils, whereas tubes are actually starting from the in part, and they skip completely the strongly connected component, and they end up in the out part. Okay, and this also is it can also be recursive, huh? So this is very weird. The strongly connected component is the biggest. It's more than 1/4 of 56 million. The in and the out parts are both slightly less than 1/4, and the tendrils and the tubes are also, if you take them all together, quite big. That's the same size as the in or the out, 44 million. Okay, so this actually is the structure of this huge graph, and it's still true today, of 20 or 30 billion pages. That's the web. Okay, isn't that kind of interesting? And we're going to say things about that, and there's things that we can deduce from that. Okay, so that's the end of the teasers. Now I'm going to start on graph theory. This is chapter 2 in the book. Okay, first I start by giving you some basic definitions. So probably some of you have already seen a little bit. Théorie des graphes, oui? Vous avez vu un peu ça? So this is partly a refresher, although the concepts we'll talk about now, some of them are different because they're the ones that we're interested in. So a graph, G, is a pair, N, E, where N is a set of nodes, and E is a set of edges. Edges, arête in French, and an edge is a pair of 2 nodes. So this would be an example of a graph with 3 nodes and 2 edges. Okay. Now there's 2 kinds of graphs. There's what's called a directed and an undirected graph. In a directed graph, the edges have directions, so they're actually tuples. They have a first and a second element, so they're arrows. Okay, the edges are arrows. And in an undirected graph, the edges have no direction, so they're actually just sets of 2 nodes. Okay, there's no direction between the A and the B here. Both of these are interesting and useful. Most of the graphs in this course that we talk about will be undirected, but not always. We'll also have some directed. So these are the 2 kinds of graphs. Okay, so that's the formal definition of a graph. Here's an example. I have carefully chosen my examples to also be very interesting by this stuff. This is a very interesting example because it's ARPANET. You can see the graph is superimposed on the United States. This is actually the birth of the internet. This is the ARPANET in December of 1970. This could be somehow considered as the birth, the first internet. TCP/IP was done here. Okay. Now you can see these are mostly universities, or there's also research organizations like RAND, UCSB, Santa Barbara University. Okay. So this is a typical example of an undirected graph. This graph is superimposed on the geography, but you can also make it more abstract. So here's ARPANET in December 1970. That's purely the topology, purely abstract with no geography. Okay, so this models a real-world structure, and you can see the different companies, so Carnegie Mellon, Harvard, UCLA, Stanford, blah, blah. There's the universities and research institutes that are connected together. Okay? Simple example of a graph. But it's nice to see the birth of the internet. Okay? Okay, let's go on now. In a graph, you can define a path, a chemin, a path. It's a sequence of nodes such that each successive pair is an edge in the graph. Okay, that's clear, huh? Each pair in this sequence is an edge in the graph. I don't know if I have to make a picture of that. It's very simple. Okay. So here's a graph. So this would be a path, A, B, C, D. Okay? Each pair is an edge in the graph. Okay? Now, this is a funny definition because in a path, the same node can occur twice. Okay? This is also a path. A, B, C, E, A, B, C, D. This would be a path, okay? A, B, C, E, A, B, C, D. Even though the node A and B occurs more than once in here, this is an example of a path. So in a path, you can actually go around and visit nodes more than once. But sometimes that's not interesting, so we also define the notion of a simple path, where each node occurs at most once. So a simple path, for example, would be A, B, C, D, but A, B, C, E, A, B, C, D is not a simple path, okay? So that each node occurs at most once. So a cycle, okay, now we go a little bit farther, is a path with at least 3 edges, such that the first and the last nodes are the same, and otherwise all nodes are distinct, different. Okay, so for example, a cycle here would be A, B, C, E, A. This would be a cycle. It ends in the same place it started, but all the other nodes are distinct. So if you don't count the first and the last node, it's like a simple path. And it has at least 3 edges, because cycles with 2 and 1 edge are not going to be interesting for us. Okay? We are not interested in these trivial cycles. So this is what we will consider to be a cycle. Notice, if you look back at the ARPANET graph, every 2 nodes here, every edge in the ARPANET graph is part of a cycle. Okay? Every edge is part of a cycle. That means there is redundancy. There are at least, between every 2 nodes, there's at least 2 different paths. Okay? Why is that important? Well, you know, of course, the reason why the internet was funded by the Department of Defense, because they wanted to communicate even if the United States was destroyed by nuclear bombs, so they wanted a network with lots of redundancy, okay? So this network has redundancy. Of course, the internet escaped from the clutches of the Department of Defense and became much more general thing. But that is an important property, okay? That gives this notion of redundancy. Okay, so let's go on. A connected graph. A graph is connected if there is a path between every pair of nodes. So that's intuitive. There's no islands sitting somewhere. So this is a connected graph because there's between every 2 pair of nodes, there's a path. But if I would have extra nodes sitting out here, then this graph would no longer be connected. So that's connected. Okay, now the notion of a component. Okay, a component is a subset of a graph that has 2 properties. So it's connected, so that means all the nodes are like together. There's a path between all of them, and it's maximal. That means you can't add any more nodes in the graph. So for example, if I had this graph, this one together with this one, all this, then this little piece is a component. This piece is another component, but this piece here is not a component because it's not maximal. You could add 2 more nodes to it and make it bigger and still be connected. So these are the 2 connections. So it's a maximal connected subgraph. Okay? Now, if we take some huge graph, we can divide it into components. That's very interesting, okay? A graph, they're like little islands, the components. And for each component, we can actually study it. Maybe you can split the component in two components by removing an edge. If I have this, for example, this is a component. If I remove one edge, then I get two components. So this is something interesting. This might be interesting. So you can analyze a graph in terms of its components and how the components are organized. Okay? So all of that is mathematical. These are all mathematical definitions. Now I will make a step to sociology, and I will talk about giant components. Now again, this is no more a mathematical definition. This is a social definition, okay, which has is less precise, but is very important. So consider a social network. All nodes are people on Earth, and there's an edge between two people if they are friends, or let's say if they know each other, okay? If they know each other, okay? Question, is this graph connected? That's the first question. I would say probably not, because there must be little islands where there's people living that have not seen humans for a long time, or even tribes in the middle of the Amazon that have not seen for generations. It might be small, but they would have no connection to any other part. Okay? Isolated islands or pieces of tropical jungle, okay? Or even some old guy some hermit living in Siberia who's very old and all his friends are dead, okay? So that also is not connected, okay? So probably not, okay? So this graph is not connected, but still, what can you say? There's still a lot of connections. In fact, what happens is, in this graph, you can find what's called a giant component. So there exists a component that has a significant, so a large fraction of all the nodes. So even if it's not really completely connected, there is a component that has most of the nodes, maybe, I don't know, 80% or something like that, okay? So this is informal. What does it mean, significant fraction? It depends, okay? Some large fraction. Now, you can reason about this. If there exists a giant component, there's almost always only one. Why is that? Assume you would have two giant components. One has 35% of the nodes, and one has 40%. Two very big giant components. But it's very easy to merge them, okay? If there were two, only adding one edge would merge them. So it's very fragile. A situation with two giant components is a very fragile situation, especially if each one of them has millions. You only need one edge there, and the two components, they become one. Okay? This actually happens sometimes. So in the real world, the collapsing giant components is important in history. It's a historical event that is significant and could be catastrophic. And it has happened in the past. One example is when European explorers arrived in the Americas, North and South America. The Incas, for example, the Aztecs or the Mayas, okay? This was catastrophic. For example, you have Spanish explorers talking to the Incas, and then they start to know each other. Well, things happen, like disease spreads and epidemics. This caused collapses, caused pandemics, epidemics of disease, and many people died, and there's huge changes. So a collapsing giant component is actually a significant historical event when it happens. Okay? It's rare, but it has happened, and this is one documented example. Okay? So the notion of a giant component is very interesting. So here's a kind of a funny example of a giant component. So this one, this is some sociologist. Sociologists are funny guys. So this sociologist went into an American high school and made a graph where each node is a student in high school, and there's an edge if those students had some kind of romantic relationship. Okay? So boyfriend, girlfriend, whatever, okay? And you make a graph for the whole student, for the whole school, okay? Now this is very weird. You have this, it's kind of like a social graph, okay? And so this is the actual graph that you came up with. It's very funny. Notice there's this one very big component, so that's the giant component. You have a lot of little graphs that are sitting around. You have 63, which are just single little pairs here, okay? Now, so this kind of is interesting because it's a real world example, okay? And you can see that there's actually a giant component, okay? Okay, so that's the notion of a giant component. Let me make some more definitions. Distance in a graph. Two nodes in a graph, how far apart? So the distance between two nodes, actually it's the length of the path between two. But you can have many paths, between A and E, you can have this path or this one. So the way it's defined, it's actually the length of the shortest path. So the distance between two nodes is the length of the shortest path. And one way to find it is to do something called breadth first search. So you start with one node, pick a node, you find all nodes that are distance 1. So they are one length away, and that makes a layer. And then you add all the nodes at distance 2. That makes a second layer. And so you have layers. And this is called breadth first search because you're looking at the graph as a breadth. And in fact, if you look at it as a tree, you're looking at the width of the tree before you go down into the depth. Okay? So this is kind of the diagram of breadth first search. So I'm on the top there, or you. So distance 1 is my friends. Distance 2 is the friends of my friends who are not my friends. Okay. Distance 3 is friends of friends of friends who are not friends of friends or friends. Okay, and so on. So that each successive layer adds only the nodes that were not in the previous layer. Okay. So here's for ARPANET. So I start with the center of the universe, which is MIT. At distance 1, there's Utah, BPN, and Link. And then I have a bunch of things on distance 2, and I have a few at distance 3. Okay. So this is a breadth first search of the original ARPANET, starting from MIT. Okay, so this is a way of computing distances if I give you a graph. Okay, so you understand distance. Now I can give you another social thing. So this is very general. I start with a mathematical definition, and then I make some kind of sociological thing out of it. And now I do the same. Now I'm going to show you something called the small world phenomenon. Okay? Remember, there's a giant component of all the people on Earth. It turns out that most people are very short distances from other people. This. In fact, less than 6. There's this folk thing that 6 degrees of freedom, 6 steps. Okay, so this actually started in the famous Travers and Milgram experiment. So this was in the 1960s, a long time ago. What they did was, they chose 300 people on the west coast of the United States. They gave them a letter and said, you have to send this letter to someone on the east coast. So that's far away, that's thousands of kilometers. But the only way you can do it is that you give it to somebody you know who you think is closer to the destination. And that person does the same. So if I'm living in the east, in west, in Los Angeles, and I know someone in Texas, which is a little bit more in the middle, when I see that person, I give them the letter, and so on. And eventually the letter ends up at the destination. Now, if you make the statistics on the intermediaries, you can see that it only takes a few steps to traverse this thousands of kilometers, okay? So the maximum here is at 6. So this is where this 6 steps comes from, okay? So the distances are kind of short, okay? So here's another analysis. This is on an actual social network on the internet. So there's many possibilities. So this is a thing called Microsoft Instant Messenger, which might still exist. And there's 40 million active accounts. There's an edge between 2 users if they had a 2-way conversation in a 1-month period. So if I talk to someone back and forth within a month, and that person is considered to be a friend, okay? And now I want to see what is the distribution of distances between 2 nodes. So here is the path length. How many hops? So here you can see what is the probability. You can see that, again, 6 hops has the highest probability, close, just a little bit less than 1. Huh? And then, of course, it goes down. There's even some very long ones, but this is logarithmic, okay? So 20 hops, and it's already 10 to the minus 8 or something. It's very, very small. So again, this shows that most distances are short, okay? And this has gone into social popular culture. There's something called the Erdős number. Now, Paul Erdős is a famous mathematician who published many papers, and there's many stories on this guy. He never lived anywhere. Basically, he squatted in his friend's mathematician house for a couple of weeks. They wrote a paper. He got kicked out, and then he went to another mathematician's house where he squatted for 2 weeks, wrote another paper. So the guy wrote thousands of papers in his life, and he got kicked out basically everywhere that he went eventually. But there's so many papers, and he's very smart, so these papers are very good. So you can define an Erdős number. It's the distance between a researcher and Erdős in co-authors. So if I am Erdős, my Erdős number is 0. If I publish a paper and Erdős is a co-author, the distance is 1. Okay? And if I have published a paper and the co-author and that person has distance 1, then I have distance 2, and so on. Turns out most mathematicians have an Erdős number maximum 5. Okay? So you see the distance is very small, and our modest rector of the university, Vincent Blondel, turns out he has an Erdős number of 2. He's very proud of that. Okay? Okay? I am not a mathematician. I'm a computer science person. Still, I have an Erdős number of 4. That doesn't really mean much. Okay? So that's something showing me the distances are small. Another one is movies. Okay? The Bacon number. If I'm in a movie where Kevin Bacon, who is some famous actor, is in the same movie, the Bacon number is 1. And so if I'm in a movie where there's an actor who played with Bacon, then it's 2, and so on. So IMDb, which is a big movie database, the average Bacon number for all actors is 2.9. It's very small. And it's very hard to find large Bacon numbers. It turns out that if you want to get 7 or 8, you have to find an obscure Soviet movie from the 1920s, and there you will maybe find somebody with 7 or 8, okay, in there. But otherwise you won't find it, okay? So this again is called the small world phenomenon. And this is a property of these social networks, these graphs. All the distances are small. It's kind of weird, huh? How can you have a graph with 240 million accounts and the distances are all 6 or less, or many of them. So this is a very interesting thing that we're going to see. But let me just stop there now. So that's chapter 2. Now we go to chapter 3. Now let's study a little bit more sociologically on social networks. Okay? Now let's focus on social networks. So I explained to you graphs. So social networks are graphs where the nodes are human beings, okay? And the edges are some kind of connection between humans, like friendship, okay? So social networks are very important in society. This is a very human thing, okay? Let's take a look. So we're going to combine graph theory, and so this is the mathematical theory of graphs, and sociology, which is the behavior of these funny animals, which are called human beings, okay? So here's one concept. This is called triadic closure. This is a typical sociological concept. Now, A, B, and C are humans, okay? A is a friend of B, which is an edge, and A is a friend of C. You see, it's almost a triangle, huh? But B and C are not friends, okay? Now, if this happens, if two people, B and C, have a common friend, A, then the likelihood they will become friends is increased. So they will probably become friends in the future, okay, if this happens. So this is a observed sociological phenomenon. So why is that? Well, they have a common friend. So if I'm A, and if I organize a party, I will invite B and C. Maybe they will meet each other and become friends, okay? So they have more opportunities to meet. They both trust A. They have common interests with A. So I'm interested in Lord of the Rings. Maybe B and C are interested in Lord of the Rings. So they have a common interest, so they become friends, okay? And also, I want that B and C becomes friends, because I have these two friends who never met. I would like them to be friends, okay? So there's many sociological reasons. But the fact is that triadic closure, so this L, which becomes a triangle, is common in social networks. Okay, so that's one thing. This will be something we talk about a lot in the course, triadic closure. Here's another thing. This is called clustering coefficient. Okay? The clustering coefficient of a node in a graph. This is the probability that two randomly selected friends of A are friends of each other. So here I have A, okay? A has 4 friends, B, E, C, and D. Okay? Only C and D are friends. So the clustering coefficient of A is, there's one link between C and D, and 6 would be the maximum possible links. Huh? If I have 4 nodes, it's combinatorics. There are 6 possible links between the nodes, these 4 nodes, okay? But only one of them is a real friendship link. So here on the left, the clustering coefficient is 1/6. Whereas on the right, I can see that E and B are friends, E and D, and C and D are friends. That makes 3 links out of 6 maximum, so the clustering coefficient is 1/2. So it's kind of telling you how dense the graph is, okay? So here's a formula. The clustering coefficient is the number of pairs of A's friends that are connected, that are friends, divided by the maximum number of pairs, okay? This gives you the probability if you pick it randomly. Huh? Notice that triadic closure will cause the clustering coefficient to increase. Triadic closure will add links. Huh? A is a common friend between E and D, and triadic closure will make E and D friends, and that will cause the clustering coefficient to increase. Okay? So clustering coefficient is telling you how dense the graph is. It's related to triadic closure. Okay? So you can predict that clustering coefficient, how it's going to evolve in the future. Okay? Here's another concept. Okay? This is called a bridge. A bridge between parts of a graph. So here I have a graph. Notice A and B. They have only one small connection. So if I remove the edge, AB, and it causes the graph to become to be two separate components, then the edge is called a bridge. Okay? So we can actually study this sociologically. Okay? A, C, D, and E are friends. These are all a small group of 4 friends on the left that are very tightly knitted. So they're all friends with each other. Okay? Whereas on the right, you have also a similar group of 4 friends around B. Okay? But A and B, these 2 little groups of friends are separate. Okay? So A knows C, D, and E very well. And they know each other very well. But the connection with B is different. The connection with B, it goes outside of this little group. Okay? That means for A, it's a source of information that C, D, and E do not have. You see that? So A, when A talks to B, A can find out things that C, D, and E do not know. So the fact that A and B are a bridge, which is a mathematical graph concept, gives you a sociological consequence, is that A has a source of information that C, D, and E do not have. That gives A something extra over C, D, and E. So A can find out that B tells A something, and A can tell C, but C does not know B. So C will not find it except through A. So that a bridge gives you extra information, even extra power if you want, extra influence. So A actually is able to do things, know things that C, D, and E cannot do. Okay, you see? So a bridge is an important thing in a sociological setting, Okay? So that's one thing. Okay. Now, actually, let me now try to make it a little bit more realistic. In a real social network, a true bridge will be rare, okay? If I have these 2 groups, and I remove this edge A, C and B here probably have some other way because they're part of the giant component, okay? So in a real social network, true bridges that cause complete disconnect are rare, okay? There's very many connections in this network. In the graph, it's a small world graph. There will probably be other paths from A to B, okay? But they'll be longer. So we would like to capture the idea of a bridge, but in a real social network. Notice now we're adapting the graph concept according to sociology. You see what we're doing? It's a little bit subtle. So we have this very nice mathematical concept called a bridge, but it's not exactly what we want for sociology, so we're going to tweak it so that it's a better definition. And the tweak is called a local bridge, okay? So we say the edge between A and B is a local bridge, okay? If A and B have no friends in common. So another way to say it is that deleting the edge will increase the distance between A and B to a value strictly greater than 2. So A and B have a distance of 1. If I remove the edge, the distance becomes a lot longer, strictly greater than 2, so at least 3, okay? So they almost disconnect. You see that? So a local bridge, it's like a bridge if you only are looking very close. But from far away, they're still connected. But they're only connected through a long path. Huh? So a local bridge is roughly the same as a bridge, but less extreme. They connect a node to another node that would otherwise be very far away. Okay? So this is a way of making the bridge idea more reasonable. Okay? Okay, now let me do a scientific experiment. Let me do a scientific experiment, and all what we saw, I'm going to use it. This is called the Granovetter problem, and it will tell us something about friends versus acquaintances. So a friend is someone that's close to you, and an acquaintance is someone you know, but you don't know them very well. They're farther away. You know them less well. Okay? Okay. So this is actually, there was a sociologist called Mark Granovetter. So this thing is from the 1960s. Okay? But now, in the internet days, it's very interesting. Consider the following problem. Now, I'm interviewing people who have changed jobs. Okay, so I'm working at Apple, and next week I'm working at Tesla because I got hired away or something. Okay, so I've changed my job. But if you interview people randomly who change their jobs, you will observe that how did they find the new job? They found the new job through acquaintances, not close friends. That means when I want to change jobs, I talk to my friends. And I say, I would like to change job. What do you think? Where should I go? And my friends give me advice. Okay? But the friends are the people I know very well. But the acquaintances are the people I know not so well. Maybe the guy working at McDonald's who I know, but the only reason I know him is because he gives me hamburgers, okay? I don't really know him very well. He's an acquaintance, not a friend, close friend. But when I change jobs, it's actually the acquaintance that gave me the good advice, and not the friends. How is that possible? Close friends, of course, they want to help you. They give you lots of advice. They have motivation. So why did you find a job from an acquaintance? It turns out in real life, when people change jobs, they found out about the new job from an acquaintance and not from a close friend. That kind of seems against intuition, right? Your friend wants to help you, and your friend is giving you advice. But at the end of the day, when you actually change the job, the new job you have, it's not one of the advice, the things that your friend told you. It's something that an acquaintance told you. It's kind of weird, isn't it? It's a little bit counterintuitive. So Mark Granovetter wanted to study that. So we're going to study that. We're going to find the reason. It's a combination of graph properties and sociology. So we're getting into sociology here, huh? Okay? We're going to use a concept called edge strength. So a strong edge is a close friend, huh? Between two nodes, whereas a weak edge is someone you know, but they're not close friend. Okay? Okay. So here is the key insight. So you have two observations, and then you have a conclusion. The first observation. Okay? If A wants to find a new job, it will be through someone connected via a local bridge. Why is that? Because the person connected on the local bridge has new information. That person has other friends. Okay? That person has access to new information. And your friends don't, you know your friends too well. The local bridge is a separate piece of the network. Okay? So that's one thing. the information comes through the local bridge. And the second observation is, if someone is connected on a local bridge, that person will probably be an acquaintance and not a close friend. That's kind of weird, huh? If you make the drawing, let me make the drawing to show what's going on here. So here I have 4 friends. This is what I saw before. Here I have 4 friends again that are close friends, and here I have a local bridge. Okay. Okay. A and B will probably be acquaintances and not close friends. Why is that? Because if they would be close friends, then there would be triadic closure. Okay? And we'll see that in the next slide. But the conclusion of these 2 things is that if A wants to find a new job, it will be through the local bridge and therefore through an acquaintance. Okay? The conclusion of these 2 observations is that the information comes from an acquaintance. So, okay, let me explain a little bit better what's going on. So here's the triadic closure again. If A is a close friend to B and a close friend to C, then it's very, very likely that B and C are going to become close friends. Okay? Okay? This is called strong triadic closure. A and B are close friends, then it's especially likely that B and C are also going to become friends. Okay? Now look here. Here's the local bridge between A and B. In the left, it's all the close friends of A. All those edges are strong. I put a little S on there. Huh? On the right, all the edges are strong, friends of B. But the edge in the middle, is it strong or weak? The edge between A and B has to be weak. It has to be weak, because if it were strong, then it would make triadic closure. If there was a strong edge between A and B, then you would create an edge between B and E, and you would create edge between B and C, and you would create between B and D because of triadic closure. Okay? Strong triadic closure would make links from B to C, D, and E, and it would not be local bridge anymore. So the local bridge means that the edge has to be weak. And that means it has to be an acquaintance. Okay? See that? It's curious, huh? So you see how we're combining graph reasoning and social reasoning. And we're going to connect this to the internet. Okay? Okay. Oh, there's a few other things I want to say, but I will not be able to say them today. Let me go to conclusion now. So now I just want to give you a general conclusion for graph theory. Remember this Granovetter problem I just talked about? Local bridge is graph theory, but strong triadic closure is sociology. And so we're combining graph theory and sociology. And this gives us a lot of understanding, okay? We really can understand it. And we're going to use this to understand the internet, okay? We will combine mathematical ideas with human beings, because the internet is full of human beings, huh? It's very strange, huh? It's not just technology, it's human, the internet. Okay? So one of the tricks we do is that we'll define a simple concept, like bridge, and then we will make it realistic. Like the bridge will turn into a local bridge. Okay? Okay, so let me stop there. So I hope that you're seeing what's going on here, this course. So this is graph theory. Of course, we're going to study many, many things. And hopefully you really will understand the internet after this. it's important to understand internet. No? Okay, that's all for today. Thank you.